This t-shirt is 50% cotton, 50% polyester. Lots of clothing is made from blends like this, and not just clothing. Sofa covers, quilt fillings, the fabric of camping chairs, lots of other stuff. And if you were to look at a fabric like this with a super zoomed in macro lens, you really wouldn't be able to tell that it's made of two different materials. That's because the fibers are interwoven incredibly closely, so closely that you really can't separate them mechanically. But with the new process that I will be testing as soon as I'm done cutting this into a zillion pieces, we might be able to separate them chemically. And that could end up changing the way that we make and get rid of clothes. Have you ever recycled a t-shirt? Yeah, me neither. Most clothing ends up in a landfill or incinerated, and that's not just true for clothes. Only 20% of all textiles are recycled. Whenever I see a headline about recycling, I immediately don't click on the article because it's either going to be clickbait or more bad news, like this, or this, or this. But then I stumbled across this paper, which describes a one-pot reaction to recycle cotton polyester blends. Now, this paper is three things. It's good recycling news, for once. It's a reaction I can try at home in my kitchen. And third, it's just a really good read as a scientific paper. Now you might be thinking, wait a second, isn't it easy to recycle a blended cotton polyester fabric, especially if we have recycling streams already set up for the individual ingredients? And the answer is no. Cotton and polyester, they are both individually recyclable. Problem is, you cannot separate the fibers to send them into their own recycling streams. And until recently, the polyester recycling stream actually destroys cotton. For example, let's look at what happens when you take a cotton polyester blend and throw it in an acid. This right here is the chemical structure of polyester. The brackets mean that it's a polymer. And what happens in an acid is that this oxygen gets protonated, which means this carbon right here is much more electrophilic, which means that a passing nucleophile, let's say water, can sneak in here with a nucleophilic attack, which kicks these electrons up, and when they come back down again, this is the crucial part, this bond right here, it breaks, which means the polymer breaks. And that gives you lots of monomers, which you can then repolymerize back into a polymer, recycling. Now let's look at what happens with the cotton. Cotton. Now, as you can see, there are brackets here, which means it too, like polyester, is a polymer. Now, I am not going to subject you to the mechanism by which acid breaks this down because it is a beast, but acid does. By the way, there are also other things that will break down polyester, like zinc chloride, for example, but it too will also break down cotton. And if your cotton is chemically degraded, that means you cannot turn it into new fibers, which means you can't turn it into other recycled clothing. So you are essentially throwing your cotton away. So the goal here is to break down the polyester, but leave the cotton intact. The nugget of information that cuts this Gordian knot was discovered way back in 1968. Did you know that in 333 BC, Alexander the Great himself tried to solve the Gordian knot challenge, except instead of untying in Japan by a group of researchers who showed, for the first time ever, I think, that CO2 could behave as a catalyst. Now this paper is only one page, but it's kind of complicated. 3 years later, the researchers published this paper, which shows a reaction that's much easier to understand and also so bizarre that it blew my mind. This is the reaction. Amazing, right? I mean, this looks like just a jumble of random letters with some apostrophes thrown in for weird reasons. This is chemical notation. Let me make this easier to understand. Hang on. So we start out with 4 carbons attached to a carboxylic acid. Let me make this easier to understand, he says. So instead of making it easier to understand, I just got it wrong. These are the correct structures. We start out with 4 carbons attached to an ester group and 2 carbons attached to a hydroxyl group. We mix these two things with carbon dioxide at room temperature, and we get the 4 carbons that were attached to the ester group become attached to the hydroxyl group, and the 2 carbons that were attached to the hydroxyl group become attached to the ester group. In other words, these things switch places. Now, this is called a transesterification reaction, and let me tell you that as a baby organic chemistry student, I learned that CO2 is pretty much an inert gas that catalyzes nothing, let alone a transesterification reaction at room temperature. If I learned anything from organic chemistry, it's that nothing happens at room temperature. Nothing. Except, of course, vinegar and baking soda. Okay, back to our headliner paper here. I would love to tell you that the researchers were aware of the work from 1968. But they weren't. It's not their fault. Very, very few people were. So they were tooling around in the lab, and they discovered that CO2 could catalyze a very specific type of reaction, which we'll come back to in just a second. And then they went and did a literature search and found the two papers from 1968, and I think I lost one. That's just sometimes how it happens in science. This is the exact reaction that they discovered. And we are reading this top to bottom because it was too wide to fit left to right. This right here, it's our starting material. And as you can tell from the brackets, it is a polymer. It's called nylon 6,6. Anyway, this down here, this is the monomer that CO2 is able to break nylon 6,6 into. No brackets, so it's just one molecule. Two important things here. First, this reaction doesn't happen without CO2. Does not happen. A completely different reaction does instead. And second, the researchers used very little CO2 relative to the amount of nylon 6,6. And those two things together suggest that CO2 is behaving as a catalyst for this reaction. So the researchers discovered a reaction that uses CO2 to break down a specific type of nylon. What's the next logical step? Try that same reaction on a different polymer, polyester, for example. And when they did that, nothing happened. So everyone gave up and went home. That is not what happened. What they actually did was try the reaction again, but this time they added a base to the reaction mixture. Now, why a base? Because this reaction had pyrrolidine, which is a base, in it. The question is, which base do you add? And really the only way to answer that question is to add them all. Not at the same time. You do the reaction over and over again with a different base every time, and then you compare and see where you got the highest yield. So that's exactly what the researchers did, and this graph shows those experiments. Now look, this is a grab bag of bases here, all right? There are strong bases, there are weak bases, there are organic bases, there are inorganic bases. And the clear, unambiguous, and surprising result is that ammonium bicarbonate, NH4HCO3, blew all the other bases out of the water. I mean, it killed them. So the reaction that worked is this. Polyester plus ammonium bicarbonate and ethylene glycol heated up for a while, and you get zillions of monomers. Start out with a polymer, it gets broken down into zillions of monomers. Now you may notice something here. This says 192 milligrams of polyester. That's not very much. It's plenty if you want to show the reaction works. But if you want this to become the gold standard of polyester recycling, you're gonna have to scale it up. So the researchers did. The next thing they tried was 50 grams of polyester, which is 260 times as much, and the reaction also worked. But remember, the original goal here was not to recycle pure polyester. We can already do that. The original goal was to recycle blended fabrics. So the researchers ran their reaction again, this time using a 53% cotton, 47% polyester fabric blend. And what they did was they ran the reaction for 18 hours and then took microscope images of the cotton fibers over time. So here they are at 1 hour, 2 hours, 3 hours, 6 hours, and 18 hours. Do you notice any difference here between the 18-hour fibers and the 1-hour fibers? No, neither do I. Visually, they look exactly the same, which strongly suggests that the cotton is not getting degraded. Let's, as a control, compare this to a reaction that we know degrades cotton, which is the zinc chloride reaction we talked about at the very beginning. Here is that set of images. And for this reaction, the researchers didn't even have to go out to 18 hours. Look, just after 6 hours, the cotton fibers are already visibly degraded. So looking at the cotton fibers under the microscope is a great start. A visual inspection is important. But it is not the only thing that matters, because these fibers might actually be degraded in ways that aren't obvious to the naked eye or to a microscope. So the researchers used a whole bunch of techniques with very complicated names, and the evidence from all of these techniques suggests that the reaction is able to degrade polyester while also leaving the cotton alone. But look, these are pretty ideal conditions, and if you want to develop a really robust reaction, you have to show that it works under less than ideal conditions. The researchers tested the robustness of their reaction in a pretty spectacular way. First, they tried the reaction with a wide variety of polyester-containing fabrics. A grocery bag that was 100% polyester, a t-shirt that was 75% polyester, quilt filling that was 50% polyester, and a sofa cover that was 47% polyester. And the reaction worked with varying degrees of success in all of those cases, which is great because it shows the reaction doesn't just work with ultra-pure lab chemicals, but also works with actual textiles you'd find in the real world. Then, and this is where things get absolutely wild, the researchers ran their reaction with all of this stuff. This right here, that's polyester cotton. We've been talking about this the whole time. But this is a Lego, acrylonitrile butadiene styrene, or ABS plastic. This is the floofy part of a shuttlecock, polyamide. This is a nitrile glove, nitrile butadiene rubber. This is from a restaurant, polyethylene. And that right there in the middle, that was human hair. Yep, it's hair. Why human hair? Because if you are recycling a sofa cover, there's gonna be hair in there. They put all of this stuff, 10 different types of plastic in all, into a pot and ran the reaction. And from this unholy mess of crapola, they were able to recover 75% of the cotton, and the reaction did not seem to affect any of the other plastics. Now, only 23% of the polyester was converted into its monomer. That is low, but I'm hopeful with some tweaking of reaction conditions, that number can get higher. And frankly, I'm amazed this even worked at all, given all the stuff they put in there. The missing piece is seeing whether you can actually recycle the polyester, which means taking your reaction product and attempting to turn it back into polyester. The researchers did exactly that, and it worked. So what they've shown here is that at least on the benchtop scale, they have a reaction that can take a cotton polyester blend and turn it into cotton, and then a reaction product that can be recycled back into polyester. The only thing that remains to be seen is whether my replication attempt worked or was, in all likelihood, an abject failure. Let's go find out. I don't have an NMR machine lying around, so I'm gonna have to check this reaction with a simple burn test. Something's happening. Look at those bubbles. If I burn this piece of fabric and there's black smoke, that means there's still polyester within the fabric and the reaction has not worked. And that is a lot of black smoke. So, failure so far, but maybe this just needs more time. 5 more hours in the special chemistry toaster oven, and hey, that is actually burning clean, which means the reaction worked. I removed the polyester from this blended shirt in my backyard. How's that for an easily reproducible result?